Okay, in this video we're going to start looking at displaying numerical data. We've looked at categorical, now we're going to go numerical. And there are quite a few different ways that we can display this data. Frequency distribution tables is the same as what we've done in categorical data, where we're just counting how many how many things we have. In this video we're just going to concentrate on histograms. We'll do these in following videos. Okay, so when we have, so we're going to focus on this one today. So when we have numerical data, it's we call each bit of data, so numerical data, each piece of data is called a score. So when we're dealing with numerical data, each specific piece of data, each measured bit of data is known as a score. And it's also, okay, so let's talk about histograms. Let's get rid of these ones. So histogram, all very much like a bar chart that we dealt with categorical data, except where our bar chart had separate bars, and I made a point of explaining that. The bar chart. A histogram has each bar connected because we are essentially measuring numbers along a scale. Try and make the same data. There we have the bars are joined together. Okay, so let's just quickly run through the features of histogram. So histogram is drawn with a ruler and carefully scaled. This was just to show what they look like. So always use a ruler. Scores, the actual data are plotted on the horizontal axis, and so the things that we measure or count go this way, and the frequency goes that way. So this is the things that these are sort of the things that we're counting or measuring, and the frequency tells us how many scores are in each little section. Okay, so it's probably worth talking about what these sections are. So we have, essentially what we do is we group our data together into little slices, and we count how many scores there are in each little slice of the thing that we're counting or measuring. Okay, so it's probably worth talking about how grouped data we have a whole range of measurements or numbers that we've counted, and then we're going to put it into grouped categories, so we can sort of see how many small scores we've got, how many medium scores, how many big scores, and it will give us some idea of how the data is distributed across the whole range. Okay, so with group data, and specifically with frequency distribution tables, because we'll start with that in order to draw the histograms. The groups can be, the notation can be written in quite a few different ways. So the example in the book is a table representing the times taken for 40 athletes to sprint 100 meters, and they are grouped in half-second intervals across the full sprint time. So we have the quickest times go from 10 seconds to 10.5 seconds, but doesn't include 10.5. The next category starts at 10.5 seconds and goes all the way up to 11. It doesn't include 11 because the next category starts at 11. It goes to 11.5 but doesn't include 11.5. So any score between 10 and 4.999999999 would be in this group. As soon as we get to 10.5, doesn't belong here, it belongs in the next category. So it's important, it's sort of what this bit means. It's important to keep track, because if you get a score that does actually fall on the boundary, you need to know which category it goes in. So this is one way of writing it. Another way of writing this same information is, I'll put it next to it, we have a few examples. We've got 10, x, so 10.5, 11. So this is using inequality, greater than, less than, and greater than, less than, or equal to. So this essentially means x, that would be our score, is in between 10 and 10.5. Okay, so this way of representing it, it's essentially the same thing. This x is our scores, and we're talking about things in this category are but greater than 10 but less than 10.5, but it can be equal to 10 but not equal to 10.5, because that's the next category. So this is another way you might see it written. Third way could just be 10 with a little line, 10.5 and a line, 11 and a line. So this means this is 10 and everything above 10, but as soon as we get to the next category, you sort of have to understand that written this way, 10.5 doesn't fit in here, it goes in the next category. In the same way, you may see it as 10, 10.5, 11, and that's all you will get. And you sort of need to understand that the higher number in each group doesn't actually belong in that group, it's everything up to that, and then we jump into the next category. The other complication with this is when we have discrete data, our groups, so referring to the example in the book, the groups go from 20 to 29, and the next group is 30 up to 39. So this is specifically for discrete. There does seem to be a little gap between this 29 and 30, although because we're dealing with discrete values, we can't have 29.5. So when drawing a histogram, although there does seem to be this little imaginary gap in between 29 and 30, we still put the bars of the histogram together. Alright, if the data is ungrouped, then the labels on the horizontal axis, this way, are positioned under the center of each column. So that would be under the center of each column. If the data has been grouped, then these numbers would be representing where the groups stop and start. The data has been grouped. Labels match the endpoints of each group, are positioned under the edges of the columns. So that's just a slight variation depending on if our data is grouped or not. Okay, so another thing we need to talk about is how we interpret the distribution of our histograms. So before I do an example, we'll just sort of try and draw some of the ways or the shapes that a histogram may end up being and explain the name of them. So histogram. So this is histogram distribution. So the first one is called normal distribution. Now normal distribution comes up a lot in nature. It's essentially when we do the graph, we have a few things at the start, and as we get closer to the middle, the data gets bigger, and then we sort of have this mirrored. So the shape is like a nice curve like that. We call it a bell curve, and that would sort of represent, so if we measured everybody's height, the middle of the graph would sort of be the average height where most people sit, and these are the really tall people, these are the really short people, but most of the data is sort of in the middle, and the further we get from the middle, the less data there is in each of those categories. So there will be questions where you need to talk about the distribution of these graphs. So the next one, squeeze it in here, is called clustered. Let's put a little graph, and this is where we do have lots of data, but most of the data fits in one group. So we can have a few little bits like this, but most of the data fits in there. I suppose an example of that is if we were to look at the ages of everyone at Hellyer College, and this group was 17-year-olds and 18-year-olds, and this would represent all the students. Perhaps we wouldn't have any of these, but up here would be all the teachers with all their, not as many representatives, but nevertheless definitely some data coming along, but most of the data is in one of the groups. Okay, next sort is called spread data. And this is where we have almost even amounts of data in each category. We might have smaller bits at the ends. And I would say the best example of this sort of data would be like if you rolled a dice 1,000 times. Then each value on the dice would eventually come up about an even amount. So if you just rolled a dice 6 times, the graph would be not quite as even, but the more you roll in the long run, you expect to roll a 1 as often as you would roll a 6, as often as you would roll a 3, etc. Okay, so now we need to talk about skewed data. We've got two sorts, and you really need to be able to tell the difference between them. And essentially one so we've got skewed. Now skewed just sort of means squashed or squashed. I think that's probably the best way to say it. So we've got skewed left and skewed right. And the issue with these two graphs is everyone gets them back to front. And the reason is skewed left looks like this. Skewed right is in that kind of shape. So, and the issue students obviously have is they look at this and they go, oh, all the data's on the right, so it must be skewed right. But the skew kind of means all the data on the left is been squashed over away from the left. So it's skewed away from the left. It's probably the best way to think of it. And skewed right, all the data on the right is squashed this way. So when the data is on the left, it's skewed right. When the data is all on the right, it's skewed left. Sort of a back to front. Bit of a weird one going on there. But as long as you understand that the skew is like skewed away. Away from left, away from right. Write that down. And the last type of distribution, which I'll squeeze in the bottom here, is called bimodal. And I'm sure you've come across the mode of a set of data before, but we will cover that. But bimodal essentially means that it essentially means that there are two scores that have peaks. So we've got this little sort of goes up, comes down, goes up again. So the bimodal means that we've got this peak and this peak. Doesn't always sort of fit into any one category. All data is kind of going to fit into one of these groups or one of these categories of distribution. And hopefully you will eventually learn to distinguish between them. Okay, so now I'm going to jump into a couple of examples. Okay, so is this example, drawing a histogram. So it says the frequency distribution table shows the contents of 40 packets of jelly beans. So 40 packets of jelly beans were bought. Somebody counted how many jelly beans were in each packet, and then this is the number of packets that had each of these amounts in them. Draw a histogram of the data. So I've sort of started setting that up. Now, because this data isn't grouped, these are just individual discrete amounts of jelly beans. Notice that I've put these in the middle of the columns. So I've divided them up. So all that needs to be done is, first one, 78, has 3. I'm just going to do, so I'm going to use a line, so the next one goes up to 6. There. The next one goes up to 8. There. A little bit. And put a horizontal line at the top. The next one goes up to 10. So this is 81, the biggest one. And then we come down to 8 again. There, just sort of eight. The next one, I'll draw that whole line in. Next one, 3, about there. I'll use this with my scale right. And the last one, 2. And there we go. There's our histogram. I would say, just looking at that we have most of the data in the middle, and it sort of gets less as we go away from the middle. I'm going to say that's normal shaped distribution. Okay, so the thing to note there was that the data wasn't grouped. It was just, so each column represents how many packets of jelly beans. This column represents 3 packets had 78 jelly beans. 6 packets had 79. And so that's that histogram. And then we've got another example. Okay, so this is the last example for histograms. Okay, so this question, I've written out the data, started to build the table, and I've got my axes ready for the histogram. So, the question says, a forester measures the girth, that's the circumference, in centimetres of 25 trees in a plantation. So that's what these numbers are. How many centimetres measured around the tree? The first question, what type of data is this? Is it categorical or numerical? Is it discrete or continuous? So they're numbers, so I think that's a pretty clear indication that it's numerical data. And because we didn't count the centimetres, we measured them, so it's going to be continuous. So part 8, all you have to write is numerical continuous data. Part B, tally the data on the frequency distribution table. That's what this is, using a group size of 5 centimeters. Okay, so what that means is we're going to have groups, and looking at the data, I think we've got an 86, 88, 83, I think 81 is our smallest. So my groups, I'm going to go from 80 to 85, but not including 85, 85 to 90, 90 to 95, and then I think 104 looks like our biggest, so we need to go up to 105. But first I'm going to assign the groups, 80, and I'm just going to say to 85. It doesn't include that. The next category, 85 to 90, 90 to 95, 95 to 100, and then 100 to 105, and that should be enough to cover all the data. So don't forget, if we get exactly 85, it doesn't belong in this category, it's the next one up. So now we're just going to do a tally. So I'm just going to go through, and whichever group these fall in, I'm just going to put a little line to work out how many bits of data are in each group. Okay, so first one, 102, cross it out so I don't count it again. That's in the 100 to 105 group. 81, 89, 95 to 100. So using that one, 100. Don't get it in the wrong group, so this is not 95 to 100, it's only about up to 100. 100 belongs in the next category. Then with this one, 95 goes in the 95 to 100 group. 90 goes in the 90 to 95 group. 3 in that group. 9 in that group. 2 in that group. 4. So when you're doing this sort of thing, just be really careful. Don't try not to rush, because it's very easy to cross one out, get distracted, and then not actually count it or count. It's easy to miss a score, easy to count it twice. I think 4 goes there. There. 2 in that category. There. 3. 3. 4. 1. 5, not this one, but that one. 96 in that one. So we've done the tally, we've counted every single bit of data, and now we're just counting how many lines we've got here. Frequency 2, 3, that's 6, 8, and 6, and I'm just going to quickly add those up because we should have 25 bits of data. That'll give me a clue if I've missed anything. 2 and 3 is 5, 11 and 8 is 19, 6 is 25. Excellent. So that is tally the data in group sizes of 5. Draw a histogram of the data. So because this is grouped, I'm going to put the numbers on where the bars, the histogram bars actually start. So we're going to have 80 to there, 85, 90, 105. We don't need that last one. So I'm going to, don't forget to label the axes. Tree girth, centimeters. 1, 2, 3, 4, 9, 10. So I've labelled my axes, I've put my regular scale in, and now we need to draw the bars of the histogram. So in the first category we got 2. So I'll just put all the horizontal lines in. Next one. Three. This as neat as I can. 90, 506. 95 to 100 has 3. And then 100 to 105. So now I'm just going to these in. Hopefully you'll see why I was. Save a bit of time and make it slightly neater. There we go, there's our histogram of the tree growth. Your histogram describe the distribution of the data. Well, I'm going to say that because we've got a small amount of the thinner trees, and as we go up the scale, apart from the really big trees, it gets bigger. I'm going to say that this data is skewed away from the left, so this is skewed left. The data is on the right, is skewed left. Okay, so that's where I'm going to leave these histogram examples, and see you in the next video.